Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X researcher and professional physicist, and today I would like to discuss with you another one of my articles. And this one is entitled A Simple Model for the Temperature Increase in the Earth's Mantle Due to the Presence of a Brown Dwarf Star in the Solar System. Brown dwarf stars are cooled-down white dwarf stars. Newly formed white dwarf stars have a surface temperature of about 100,000 Kelvin, whilst a brown dwarf star that mainly emits infrared radiation will have a surface temperature of about 1,000 Kelvin or less. And at this temperature, it will emit mainly infrared radiation. And we can see that from the black body spectrum here. All objects, at 1000 Kelvin, this object will still emit some radiation in the visible light band, which we see here faintly. So there is a little bit of emittance in that band, but the curves below that, say the 500 Kelvin, definitely do not emit any visible light. So an object with a surface temperature of 1000 Kelvin will emit a little bit of visible light, but most of its radiation will be below visible light frequency, so mainly infrared. The sun, we can see here, this is the temperature of the sun. So this is the curve for the sun, and most of its light, as you can see the peak here in the spectral radiance, is in the visible light range, and this is the surface temperature of the sun of 5,777 Kelvin. Now, since brown dwarf stars are basically cooled down white dwarf stars, they share some of the characteristics of white dwarf stars, such as the very strong magnetic fields generated by these objects. A white dwarf's magnetic field is proportional to its angular momentum. And the angular momentum is given by the mass of the object times the radius squared of the object times basically the angular velocity. So what is most important is that it is proportional to the radius of the object squared. So the star's radius usually decreases by a factor of 100 from the time it runs out of nuclear fuel to the time the white dwarf is fully formed. Thus, the star's angular momentum would increase by a factor of 100 squared. So a main sequence star with an initial magnetic field strength of 100 Gauss will end up as a white dwarf star with a magnetic field of 100 squared times 100 Gauss, which is 1 million Gauss. Now this corresponds to a magnetic field of 100 Tesla. The magnetic fields of white dwarf stars can, however, be much higher than this. White dwarf magnetic fields of up to 100,000 Tesla or 1,000 times larger than 100 Tesla have been measured. So now we're going to model the magnetic field, and we have therefore this equation. And we are going to say that the magnetic field, which is denoted by B as a function of time, is given by B. Here it's a constant times C0, which is a parameter, times cos of omega t. Now C0 we're going to set as a parameter which will will take the distance between the brown dwarf and the Earth into account. We're going to set B to be 100 Tesla, the standard magnetic field of what a standard white dwarf star would have. Omega is the angular frequency due to the star's rotation. So for a star over a period of rotation of 27 hours, and usually these objects are fast rotators, and that goes along with the increased angular momentum. So then its angular frequency would be 2 pi over t, where t is the period, and we set that to be 27 hours. And that gives us omega, the angular frequency, as 6.5 times 10 to the minus 5 radians per second. Now we're going to let C naught equals R naught over R, where R naught is just another parameter, so we have correct units. And R is the distance between the brown dwarf star and the Earth. And we're going to set that to be half the distance between the Sun and the Earth. In other words, 7 times 10 to the 7 kilometers. Now the Earth is made up of different layers. And the layer we are interested in is the fluid core layer or the liquid core. The others are the mantle, the crust, and the solid core. Induced currents are produced in the fluid core. So we are going to assume that the brown dwarf star induces a current in that fluid core. Now, the Earth's fluid core or liquid core has a radius of, from the center of the Earth, of 3,500 kilometers. So we set RLC, where LC stands for liquid core, to 3,500 kilometers from the center of the Earth. To make the model as simple as possible, we will assume that the currents will occur in one single thick loop. This is illustrated here in this figure 3. So this is the Earth's core, it's solid iron core. This is the liquid core, and we are going to assume that the brown dwarf induces a current in the liquid core, and that it looks like a single loop current. Then the current induced in the Earth's fluid core is given by Faraday's law, which we can write as the induced current I is equal to minus 1 over R, where R is the resistance, d phi by dt, where phi is the magnetic flux. Then with the help of equation 1, we obtain the following maximum current. I equals pi RLC squared over R, C naught B omega, where this comes from the area of the loop, which is just the area of a circle. And the rest comes from the magnetic field, which is we differentiate to come up with the maximum value. Then the liquid core's conductivity has been measured to be sigma equals 1.5 times 10 to the 6 per ohm per meter. So the resistance will then be given by 2 pi RLC over sigma d squared. Then d squared is the cross-sectional area of the current loop. When it is taken to be a square of side d in this model, we will let d equals half of RLC. So we're going to make a thick loop with the cross-sectional area to be half of the radius of the loop. Then the maximum current will be given by I equals 1 over 8 sigma RLC cubed C naught B omega. Thus the power generated will be, and power for a current flowing through a circuit where resistance R is I squared R. So then using the values we have for the current and for the resistance, we obtain the power to be 1 over 8 pi sigma RLC to the power of 5 C naught squared B squared omega squared. And assuming that heat is dissipated through a shell of area 4 pi RLC squared and thickness a half RLC, we get a temperature increase transferred to the Earth's mantle of delta T, so that's the increase in temperature, is the power divided by 8 pi K RLC. And we case the thermal conductivity of the Earth's iron core, which is estimated to be 44 watts per meter per Kelvin. Then the expected temperature increase is given by delta T equals, and remember we now know what power is, what the P is, stands for power, it's given by this equation. So when we plug in all the values, this is what we obtain. Sigma RLC to the power 4 C naught squared B squared omega squared over 4K. And when all the values are inserted that have been given, For example, the conductivity K is 44 watts per meter per Kelvin. We obtain 690 Kelvin. Now, since the temperature in the Earth's core is 5,700 Kelvin, the above result indicates a 12% temperature increase. This is a significant increase, which should cause the mantle to expand and thus place the crust under pressure, which will in turn lead to earthquakes and increased volcanic activity. I am Dr. Claudia Albers, Planet X physicist. Thank you for watching.